Good morning. Once again, welcome to physics. Can get the material, the notes, can get it from the Facebook. Right? Download the notes from Facebook, PowerPoint, and the video. And today's lesson we'll be looking at partial paper. Right? So you can get the topic by topic from 2001 to 2010 to practice, try out. Just make sure that you know how to answer the question before you go for the exam. Or you don't have Facebook account, can go to YouTube. Day one will be download under A-level revision 25 binding energy. Okay, let us make a start. Okay, today's topic A-level revision 26.3 nuclear physics binding energy for Cambridge. Right? The picture all this summarize for you what is to be covered. Right? First, look at what is given. Elementary charge, atomic mass unit, mass of proton and mass of electron is given in your data sheet. Okay, the first thing to remember is electrostatic and gravitational force between nucleons. Right? Nucleons are your protons and neutrons. Proton are positively charged. So when proton come together, there's an electrostatic repulsion. And this force can be quite large as the proton get closer together. Force of gravity between proton is negligible, very weak, very weak. That usually when we study electrostatic, we don't bother about gravitational force. And proton is also small. Mass of proton is very small. Then we come to, there must be another force in the nucleus. We call it nuclear force. And this force is strong attractive force. Short range, that means it is only strong within the nucleus. Outside the nucleus, it tends to go very fast to zero. And it exists between nucleons, holding the nucleons together, either proton and proton or neutron and proton. So whether a nucleus is stable depends on the two forces, nuclear force and electrostatic force. Okay, so electrostatic and nuclear force together determine whether the nucleus is stable. An unstable nucleus decay to a more stable nucleus. Where the nuclear force is present, there must be energy required to separate the nucleon. Right? Because just like the positive and negative charge there, if we want to separate them, we need energy to separate them. So if there's attractive force, there must be energy required to separate them. What is binding energy? Binding energy of the nucleus is the minimum energy required to completely separate the nucleons of the nucleus, or energy release when the individual nucleons come together to form the nucleus. The larger the binding energy, the greater the measure of the attractive force inside the nucleus. Another term that we need to remember is mass defect or mass excess. The mass of the nucleus, right? Nucleus, where the nucleus form together form the nucleus, is less, right? This mass is less than the mass of we add up the total mass of the nucleons. The mass of the nucleus is smaller. So the difference in mass, or we call it mass defect or mass excess, is the difference in mass between the total mass of nucleon in the nucleus and the nucleus. Right? So we usually like to write in mathematical equation. It's easier to understand. This one tells you that number of neutron times the mass of neutron. Number of proton, Z, times number of proton, minus the mass of nucleus. And that is the mass defect. Right? Total mass of nucleon, and that's the mass of nucleus. Right? A is the nucleon number, Z is the proton number of proton or number of positive charge in the nucleus. So Einstein gives us the equation to calculate binding energy. Right? Einstein's relationship, E equals to delta M times C squared. Delta M, and this energy is released when the nucleons come together to form the nucleus. So E is energy in joule, delta M is mass in kilogram, C is the velocity of light, 3.0 times 10 to the power 8 meter per second. One of the constant given in the data sheet. Or we can also show that mass, one atomic mass unit equals to energy 931 mega electron volt. Right? This one is a faster conversion rather than using this equation. You can remember that, but usually they will ask you to derive and then use this value to calculate. Binding energy per nucleon is defined as the total energy needed to completely separate all the nucleons, same as before, binding energy, but we divided by the number of nucleon nucleus. This allows us to compare the binding energy per nucleon for each nucleus. Right? So it's binding energy per nucleon is just the binding energy, which is represented as E divided by the number of nucleon. Right? So this quantity allows us to compare the stability of the nuclei of different elements. Then we can draw roughly the shape. Right? Don't need to really know the exact value. Sometimes they will give you, sometimes they won't. That's roughly the shape there. Right? Most of the nuclei value is about 8 mega electron volt. The smallest is deuterium, 1 proton and 1 neutron. And then the highest point, the maximum binding energy per nucleon is your iron, A60, and uranium-238 is the last one. Iron being the most stable. Sorry, it's a wrong spelling. Yeah, iron is most stable because it's the most binding energy per nucleon. Nuclear reaction. Right? We can write it as like chemical reaction. Right? That's your equation. A small a plus capital A give you B plus small b. And A small a and big A is the reactants, the two that combine initially. And B plus small b is the product, what you get at the end after the reaction takes place. A is usually, the capital is usually the target nuclide. The small is the incident particle, that means a projectile, something which sent to hit the target. And then B is the final nuclide, the result of the reaction. And then the emitter particle will be small b. Right? Example, we send alpha particle, A, small a, to nitrogen, the A, and then after the combination, O is the final nuclide, and then the proton is the one that's emitted in the reaction. Right? So we have small m subscript A, mass of incident particle A, and M capital A, mass of nucleus A, M capital B is mass of nucleus B, M small b, mass of emitter particle B, and then E is energy, either release or absorb. Q, right, we define as the total mass of reactant. Remember, it's the reactant minus the mass of product. Subtract that, and then times C squared. Right? Or in terms of symbol, mathematical symbol, if we work with mass. But if we work with binding energy, then we have to work with binding energy of the product, right? And then product minus binding energy of reactant, the other way around. Q is a measure of the energy release or absorbed in a reaction, in a nuclear reaction. If it's positive, it means the energy is released. That means the reaction can take place. Negative means energy is required. That means if I want to have this reaction take place, I must send this A, the projectile, with at least the minimum kinetic energy before this reaction will take place. Okay, so negative means I need to give energy to the projectile before the reaction will take place. By itself, the two A and capital A will not take place. Nuclear reaction, we look at an example. Right? So we send an alpha to hit a nitrogen atom, and then we produce oxygen and proton. And we look at the total mass of the reactant, that one, alpha and nitrogen, and the total mass of the product. We can see that the mass of the product is greater than the mass of reactant. That means this mass there is greater than what we have initially. So it means that the reaction cannot take place. To make the reaction take place, the alpha particle must have enough kinetic energy. And we can calculate that energy required by calculating the mass difference. Right? Mass of reactant, total mass of product. Subtract that, we get a negative sign. So we can see from here the reaction will not take place. And we use the conversion factor, atomic mass unit, 931 to get magnetic electron volt. So it means that the energy required for the reaction to take place is 1.20 mega electron volt. So the alpha particle must have this minimum energy before the reaction can take place. Then we look at fission. The neutron is sent to hit a uranium-235. So usually fission occurs where the original heavy nucleus, this heavy nucleus, splits into two approximately equal half. Two approximately equal, not exactly equal, but roughly, to form two products. And then sometimes release of energy and maybe some other neutrons. Right? Usually uranium-235 absorbs a thermal neutron, right? A slow neutron, split into two different nuclei. Right? For example, beryllium and krypton, they are completely different from uranium. Right? So there's a thermal neutron goes into. So we can show the picture what is happening on the binding energy per nucleon to nucleon number graph. Right? In fission, there is an increase in binding energy per nucleon of the product, EA and krypton. There's an increase compared with your uranium-235. So we can see that binding energy per nucleon of the product is greater than binding energy of uranium. So the reaction can take place with the release of energy. And nuclear fusion, the same thing. Right? In this case, we have two lighter elements. In this case is tritium and deuterium. They are forced to combine, and then they produce helium and neutron, and energy is released. Okay, so tritium and deuterium are what we call heavy isotopes of hydrogen. Likewise, we can also show that. Right? Can show on the binding energy per nucleon against deuterium graph. Right? The reaction, there's your deuterium, there's a tritium, and there's a helium. So we can see the same thing. Binding energy per nucleon increases. So that's an energy releasing process. Right? So for fusion to occur, the binding energy per nucleon of the product is helium, is greater than the reactant. The reactant will be a tritium and deuterium. So let us just summarize before we try some example, some partial paper. Mass defect. Energy release when nucleons come together from the nucleus. And the mass defect, we know that the total mass of nucleon minus the mass of nucleus. And then to calculate the binding energy, we take the difference in mass times of C squared. And binding energy per nucleon, we divide the binding energy with your nucleon number A. Large binding energy per nucleon means large nuclear force, so more stable. Okay, we come to fusion and fission. And we measure the energy release as Q, mass of reactant minus mass of product. And all this together, subtraction, we times C squared. Or we use binding energy of product minus binding energy of reactant. Remember, if you use binding energy, you have to use product first minus the reactant. And it's positive, it means the reaction can take place. Negative means I have to give energy for the reaction to take place. Okay, let's try the first question. On figure 8.1 shows a variation with nucleon number of binding energy per nucleon or nucleus. So that's a binding energy per nucleon. That's a nucleon number. On figure 8.1, mark with S the position of nucleus with greater stability. So you should be able to remember that. It's the top there, S. Then the next part. One possible fission reaction, right, is given you. Possible product. On figure 8.1, mark a possible position for uranium-235, call that U. Right? Usually it's quite over the end there, 238 there. And then krypton, right? If you want, you can roughly estimate. Right? This is 60. This is 235. Then you divide equal parts. 120. Take this as 240. Don't have to be exact. You want roughly the approximation. So this is 180. 180, you want krypton. Krypton is about 90. Right? So 90, roughly about there. About there. Maybe your krypton should be further down there. If you are very particular, examiner are not that particular. As long as you get roughly the position right. Yeah, okay. So if you are very particular, right? Should be somewhere there. If you are very particular about, as long as it's not here or too far away, then you should be all right. Okay. right? Make a rough estimation. They don't expect very accuracy. If you put your krypton here, then you will be in trouble. Right? S must be at the topmost there, not at this part, not at that part there. Use the data, right? That's your data. Right? Remember this binding energy per nucleon of each nucleus. To calculate the energy released in the fission reaction, give your answer to 3 significant figure. Right? They want 3 significant figure. They want you to round off to 2. Okay, so we are starting with energy. So we have to start with binding energy of the product minus the reactant. Right? But remember, we must multiply the number of nucleons. So energy release is binding energy of product minus binding energy of reactant. This is the product. This is the reactant. Product 144. Right? Look at the energy. This is the energy 144 times that. Right? I take the minus 12 out. And then krypton Kr 90 times that minus, right, minus 12 is taken out, minus your 235, this is your 235 times your that value. Remember this per nucleon, so we have to multiply by number of nucleon, 235, and then we get a value, positive value, means the reaction can take place. Okay, 3 significant figure. The mass equivalent, basically they're trying to get you to use all the formulas that they expect to remember. E equals to mc squared or delta m, doesn't matter. Okay, put in your value that you have just calculated. That's the m, that's the speed of light. On a data sheet, you calculate your m in kilogram. Suggest why neutrons are not included in the calculation. Neutron doesn't have binding energy. It's a single particle. It doesn't combine. It's just by itself. Right? This one, question 11, 205 November. Right? Same thing. Illustrate the variation with nucleon number A. Binding energy per neutron varies with A. On the figure, mark S, the region of the graph represented nuclei having the greatest stability. That's what we want. Highest point. Explain what is meant by binding energy of a nucleus. Memory work. Energy required to separate the nucleons in a nucleus completely. Term must be like completely. They don't have any more attractive force anymore when you separate the nucleon. It's far away. Uranium-235 undergo fission as a neutron. When bombarded by a neutron to produce xenon-142, strontium-90 as shown. Determine the number of neutrons produced in the fission reaction. So how to do that? Right? Work with conservation of nucleon. Right? 235 plus 1 equals to 142 plus 90. And then we find X is 4. I think that's good enough already because they already told you it's neutron. So it's 4 neutron. You want to check that it's true, then you can add your, right, that it doesn't have a charge. 92 plus 0, that's the initial total charge. 54 plus 38, that's your total final charge. And then you put a charge for the neutron as Z, you calculate out the Z is 0. So it must be a neutron, 4 neutron. Right? You can see the calculation. By now, they want you to calculate binding energy again. Right? Just now given in joule, now it's given in mega electron volt. So you must be familiar with all the different units to calculate. The energy in mega electron volt released in the fission process. Okay. So we remember when we work energy, we work with product first. Binding energy of product minus binding energy of reactant. So product, remember this per nucleon, and there are 142 nucleon. So 142, right? Remember the 142 times 837 837.142 and 872 times 90. And then product is your the reactant is your uranium-235, right? That's the number of nucleon times the energy per nucleon right there. And use your calculator, subtract it out, calculate out 190 mega electron volt. Right? Same. That is what we have calculated. They want you to use the formula. And then remember, this is not given in a data sheet, but remember the definition of electron volt, right? Is the energy required to accelerate an electron through 1 volt. So the value is the same as the charge of the electron. Then you can convert 1 mega electron volt equals to 1.6 times 10 to the power minus 19. Okay, and then times 10 to the power 6 here, and 10 to the power 6, so you get 1.6 times 10 to the power minus 13 joule. From that equation, you want to find M, take the C square down. So that is the energy in joule, right? 190 mega electron volt, change it to joule, times that, divided by speed of light square. Use your calculator, calculate out in kilogram. Explain what is meant by binding energy. That is memory work. Right? The easy mark to gain, they were very kind to you. They wanted to see whether you can memorize. You can memorize if you get this point. Energy required to completely separate the nucleon in the nucleus. Sorry. On figure shows the variation with nucleon number, right? A of the binding energy per nucleon of the nuclei. EB is a binding energy per nucleon. One particular reaction, right? This particular reaction on 7.1 label approximate the position of uranium. Okay, uranium, beryllium, krypton, roughly that. The neutron that is absorbed by uranium nucleus has very little kinetic energy. Explain why the reaction is energetically possible. Binding energy is calculated by taking our nucleon number times our binding energy per nucleon. And we find that for the reaction to take place, right, binding energy of product must be greater than binding energy of the reactant. That is what happening. That's why the reaction can take place. Beryllium-141 has a half-life of 80 minutes. Right? Sometimes they combine binding energy and reactivity together, so they can test you both topics together. Half-life of krypton is 33.0 seconds. In the fission reaction, the mass of uranium-235 equal the numbers of beryllium and krypton nuclei are produced. It means that krypton and beryllium are produced by uranium. Estimate time taken after the fission of the sample of uranium for the ratio number of beryllium-141 nuclei divided by the number of krypton-92 nuclei to be approximately equal to 8. Right? The time for that ratio to become 8. So first thing to remember, they give you half-life, they want you to find lambda first before you can use the equation. You can go to data sheet or formula sheet, get this, and if you can remember, so much better. Right? So calculate for krypton and calculate for, there's your krypton, there's your beryllium. Calculate that out using this formula, and then use this formula, N equals to N naught E minus lambda T. So the number present initially of beryllium and krypton are the same because they all came from uranium-235. Right? And we know it's 8. Right? So that one is for beryllium. This one is for krypton. T is just the time. Okay, put in your value, this value, and that value there. Yeah. Yes. B, 2, 3 is this, sorry, B minus, and then when we take it out, it becomes minus, minus becomes positive. So it's 2, 3, 1. And then that minus is this one, the one there. Change it to the same number of decimal place, easier to see. Then use your calculator, you get 9.0 seconds. Okay. Okay. A positron, there's a positron, is a particle that has the same mass as the electron, or we call it antiparticle. And there's a charge, both of them have the same charge. Same, one is positive, one is negative. Positron will interact with electron, we call it annihilate, to form 2 gamma ray photon. Assuming that the kinetic energy of the positron and electron is negligible when they interact, right, we don't bother. Right? We probably have to send kinetic energy for the proton, positron, and electron to combine each other, so we don't bother. And assume it's negligible. Suggest why 2 protons will move off in opposite direction with equal energy. So now they are testing you about AS, conservation of momentum. Right? So this is a collision question. Since momentum before combination, before they combine, is 0, momentum must be equal and opposite. Right? Initially, they are 0. So finally, they must be moving in opposite direction, either this like that or like that. Right? One go up, one go down, or one go that way. Equal and opposite. After combination, since the gamma ray have the equal momenta, so the momenta photon energy must be equal. Okay, so we can think of the photon as particle. Calculate the energy in megaelectron-volt of one of the gamma ray. Remember that the positron and the electron combine to form 2 gamma ray photons. So we just need to calculate for one of them. Use either a positron or electron. Same, E equals mc squared. That's the mass of electron can get from your data sheet and the speed of light. And then when we want to convert it to mega electron volt, right? 1 mega electron volt is just that. So we have to divide to get our mega electron volt. Okay. Sometimes they also can combine your electric field question and nuclear physics together. Right? It's good because they can test you 2 topics together. So you got your deuterium traveling directly towards one another, both of deuterium, initial velocity v, right, coming together. When their separation is large, that means far away, no force at all. Compare with their diameter, they each have a speed v. Right? No force there, that's the speed they have. Diameter of the deuterium is this one. Remember, when they are touching each other, that diameter becomes the separation between the center to center. Use energy conservation to show that the initial speed of deuterium nuclei must be approximately that in order that they may come in contact. So they just want the distant or closest approach where the nuclei just contact each other. So the center to center is just the diameter. Explain your working. So deuterium has 2 nucleon, remember that, 2 nucleon. one positive proton and one neutron. And then this diameter becomes your distance of closest approach. Right? And then we need to remember potential energy. Right? Potential energy is given by this formula, Q square 4 pi epsilon naught R. Right? Where you can get the potential energy for this nucleus from the formula sheet there given. And then you just multiply by the charge of the others one. Both of them have a charge Q. So basically, it's a conservation energy. Right? These two have kinetic energy. They come together, and when they touch, then there will be a gain in gain in electric potential energy. So just put it there. There are two of them. So it's half NV squared times two of them. One is deuterium and one that deuterium. And then the potential energy will be Q 4 pi epsilon R. Q squared divided by 4 pi epsilon R. Okay, put in our value 2 half. And then this one, right? Mass, remember, this is the mass of deuterium. Deuterium, in this, the examiner use a mass of proton. Consider the neutron as a proton. But I would rather use atomic mass unit, which is the average mass of a proton and neutron in carbon 12. Right? I would rather that, but slight differences only. Times 2 because there are 2 neutrons times the speed. Right? And this is the charge on the deuterium, charge of electron, positive charge. Each of them have positive charge. Square that, and then all this value epsilon naught can get it from the data sheet, and then that is our R, distance of closest approach. So we can show is equals to what we are supposed to show. For fission reaction to occur, the deuterium nuclei must come in contact. At least they must come in contact. Assuming that deuterium behaves as an ideal gas, deduce a value for the temperature of the deuterium such that the nuclei have a root mean square speed equal to the speed calculated. Right? So take the speed as equal to root mean square speed. So this question is good because it combines 3 different topics. Nuclear physics, binding energy, they combine electric field, electric potential energy, and now they use ideal gas. Okay, so you don't need to remember the formula, you can derive it. PV equals to 1/3 nm V squared or C squared. Then PV equals to NKT. N is the number of particle. K is the Boltzmann constant. T is absolute temperature. M is the mass of the particle. So we can combine them. Right? This is 1/3 there. Right? PV is the same. So it's NKT. Cancel the N. So the N, we still got 1. Right? Take the 3 across there, we got MV squared and 3KT. K is your Boltzmann constant. You can get it from the data sheet, the value. And put into this equation, we just times half to get a kinetic energy, and divide by half here, you get this formula. Right? Then get the formula sheet there. Right? That's the rest mass of proton. Put it value in. Right? As I say, you can use 1.66 if you want to. The unified atomic mass. That value, unified atomic mass, instead of 1.67. I think they're more interested in how to calculate rather than particular about the exact value. So slight differences they don't mind. Right? And then that's your speed. And we have just shown 3/2. That one is on the data sheet. Absolute temperature T. So that's how we estimate the temperature that require for the 2 deuterium atoms to come in close contact. They must have that temperature before nuclear reaction will take place. Right? So that temperature is very high. Cannot get it on Earth. You can only find it in the sun or the stars. Right? So that's the comment. It's a very high temperature. Can I find this type of temperature in the stars? That's why the reaction can take place in the star or in the sun. Okay, let's try something different. Now fusion. The control reaction between deuterium and tritium has involved ongoing research for many years. Where is research? Because we want to produce energy. The reaction may be summarized. They've given you the equation, and Q is the energy that is expected to be released. And they give you the binding energy per nucleon, remember, per nucleon. Right? That is your deuterium. That's your neutron, don't have binding energy. And then the helium, 707. Suggests why binding energy per nucleon for neutron is not quoted because it is not combined. So it doesn't have binding energy. It's a single particle, single neutron. It must combine with a proton, then it will have binding energy. Calculate the mass defect. Okay, so you will probably be wondering how to calculate that. But they have given you the binding energy. So they wanted to work backwards. Okay, so from binding energy given, right, there are 4 new nucleon, right, 4 nucleon. So we must times 4 this one. And then change it to joule. Change it to joule. Okay, that's your 4 nucleon. That's your value because that's per nucleon in mega electron volt. And then 1, right, remember 1 mega electron volt is 1.6 and 10 to the power minus 13 joule. Right, refer to the previous question that we have calculated for you. And use your calculator to calculate the value in joule. And we want to find the mass defect. Right? C is given in the data sheet. Binding energy is what we calculate here. Put in your value, calculate your delta kilogram. They are very kind. State the name of the type of reaction illustrated by this equation. Fusion. That's simple. Easy mark to get. Nuclear fusion. Okay, so it basically taking you through calculate how to use the formula E equals mc squared. Now they want you to go into the reaction. Determine the binding energy per nucleon of tritium. Okay, this is the one that is not given. Right? This one is given, this is given, and that energy is given, 17.7 mega electron volt. So remember, we work with energy, it must be the, right? Let the binding energy per nucleon of tritium be X. This one, we don't know. We want to find that, let it be X. Then Q, right? We define as binding energy of product, binding minus binding energy of nucleon. So it's, right? That is your Q, 17.7 mega electron volt times that value, right? There are 4 nucleon, the value times 4. And then this one, 2 nucleon. Deuterium got 2 neutron. That is a value for deuterium times 2. And then tritium, we don't know the binding energy per nucleon. Right? So we times 3 because there are 3 nucleon. And simplify, we get 2.78 mega electron volt per nucleon. Okay, so that's the end. Thank you. As I say, this will be available in YouTube or Facebook.